Good afternoon, good evening, and good morning to all. So first of all, I welcome you to our monthly lecture series in field monitoring and geomechanics in the TC220. And I'd like to welcome all of you to this lecture series. And thanks for joining. And today we have a very interesting lecture by Skevi, Dr. Skevi. And a very important topic, very relevant to most of the countries, developed countries or developing countries as well. So I'm very eager to listen to her. And with this, just introductory, I would like to request Dr. Andrew, our chairman of this TC committee of ISMG, to just speak a few words.
Okay, thank you very much, Neelima, and welcome everybody again. It's great to see this series of lectures growing, and it's an amazing effort that's been put in by Neelima and her team in India. I don't want to say too much at this stage. I can come back at the end and give a few notices, but I think I'm pleased to see Skevi giving a talk on her subject, which I think is extremely relevant in the modern age that we're working in, and an extremely valuable tool of INSAR. So I'll hand over to Skevi and look forward to learning lots about this this new technology, or really not so new, but certainly being exploited a lot more these days. So thank you.
Yeah, thank you so much, Dr. Andrew. So before actually starting, I would like to introduce Dr. Skevi to today's speaker, and it's my honor to introduce her. She holds a bachelor's and master degree in civil engineering and geotechnical engineering, and a PhD in satellite remote sensing from the University of Southampton. And she specializes in the application of satellite remote sensing technology for the civil and the geotechnical projects. She has more than 20 years of experience in the different aspects, especially in teaching, research, and also in the practice on several observation techniques. And she's also technology manager at Geofem and the leading satellite and remote sensing company. And her work is focused basically on developing techniques to assess some of the susceptibility of infrastructure assets to geohazards. So thanks, Dr. Skevi, for accepting this talk. And with this, a very brief introduction, we are recording this lecture, and it will be posted in different, social media platforms and TC220, LinkedIn, everywhere. So kindly follow us, and also IGS, Indian Geotechnical Society YouTube channel we have. And so please do follow, so that you do get a lot of updates, and you can look back to the previous recording lectures and other repositories. So thank you so much, and over to you, Skevi. Kunal, can you stop this screen?
Okay, so thank you very much for inviting me to this series of lectures. It's nice to be here, and let me share my screen. Okay, so I hope you can see my screen. So let me start this lecture on the use of remote sensing, and particularly INSAR, for the built environment, and I will talk about its use and application on geohazards, and also for monitoring infrastructure assets. So the contents of this presentation, I will start with explaining a little bit about the basics of satellites and how they work. And then I will present a lot of examples and case studies for monitoring infrastructure assets. And then I will show you how we use the outputs, not only from INSAR, but also from other satellite sources with AI for development of susceptibility assessment to geohazards. A few words about who we are and what we do. We at Geofem were established in 2007, and we specialize in geotechnical engineering, satellite remote sensing, and GIS, and combining all these three disciplines for maximizing the resilience of infrastructure and the built environment. Now, I always start with this slide just to show the importance of developing new techniques for monitoring infrastructure assets. We face many challenges in infrastructure, such as the aging of the infrastructure, with most of it being more than 50 or even 70 or even older than that, 50, 70 years old. We have heavier use of the infrastructure than ever before. We also have settlements of populations into hazardous areas, therefore construction of transportation networks going through hazardous areas. We have climate change, which impacts the occurrence of geohazards, declining budgets of the managing agencies, and also shortages in the engineering personnel. For all these reasons, it's becoming more and more important to have techniques for monitoring our infrastructure efficiently and effectively. So I will start with some basics of how the satellites operate. So we have here the geostationary orbit satellites. These are satellites that, as the word says, geostationary. They remain stationary compared to the rotating Earth. And they are used for observing the development of specific events on the Earth's surface. So they are observing the same event. We also have the sun-synchronous near-polar orbit satellites, and that's what SAR satellites use. So they are orbiting from the North Pole to the South Pole to the North Pole. So if you consider this rotation with the rotation of the Earth, we get global coverage. So in that way, we have global data for, especially since 2015 onwards, from the Copernicus European Space Agency program. These satellites, the SAR satellites, they revisit the same location on the Earth's surface at the same time of day every few days. We also have the ascending orbit and the descending. So ascending is when the satellites are obtaining data while traveling between the South and the North Pole. And descending is when the satellite obtains data while traveling from the North Pole to the South Pole. And this slide shows it better. So in an ascending orbit, this is our satellite traveling in that direction. So you can see it's scanning this part of the Earth surface. And in a descending orbit, shown in orange, it's scanning this part of the Earth surface. And why am I showing this? The importance of this is that we can have the same area on the Earth's surface obtained from an ascending and from a descending geometry. And the importance of that is that if we have data from ascending and descending orbits, we can decompose them and get our displacement into vertical and horizontal direction. But because the satellites are traveling from north to south and they obtain data from the east, you can see that the horizontal component is always only on the east-west direction. What I want to show here is what SAR stands for, SAR or INSAR. We are all, we have heard this term. So SAR stands for synthetic aperture radar. R because it operates in the microwave portion of the electromagnetic spectrum, and it's different to optical data. So our satellites do not rely on sunlight. Instead, they send out their own electromagnetic radiation and they measure what is reflected back to them. A stands for aperture, which is another word for the another term for the word antenna, and S stands for synthetic because to have a good spatial resolution, this antenna would need to be very large, very long. This is impossible in practical in space. So instead of that, we have a smaller antenna, which simulates the behavior of a larger antenna by taking a sequence of acquisition. That's a word from SAR waves. We measure two main properties. We measure the amplitude of the waves, and I will show you in this presentation how we associate the amplitude with volumetric soil moisture measurement. And the phase difference between successive passes is converted into displacement measurement. And as geotechnical engineers, we know the importance of soil moisture and displacement into assessing the condition of the ground and the infrastructure. And with this slide, I want to show how we convert phase difference into displacement. So we have our satellite here, sends out electromagnetic radiation, hits this building with a blue wave here, and then it measures what is reflected back, the phase that is reflected back. A few days or weeks later, the same satellite passes and sends out electromagnetic radiation. But imagine that this building has moved to this new shaded area shown here. So we have the red pass now, the red wave, hitting this building in this shaded area, and it is reflected back. So what we notice is that there is a phase shift between the first and the second pass. And if we have a large data set of such measurements, we can convert this phase difference between the successive passes into movement with millimetric accuracy. And the advantages of this technology is that this is a very economical solution. It's very fast compared to visual inspection, more accurate to visual inspection. There is high frequency of data. It's a non-disruptive method, it's automated, and is the only method that offers retrospective analysis because data exists, as I said, for most parts of the world since 2015 or a bit later. You can go back in time and see the trends that are developing for any project. And I will show you some examples now. So I will start with this landslide. This is a landslide that has been actually mitigated through installation of piles and a retaining wall. But what I will show you is that we are monitoring, we have monitored this landslide after many years of the mitigation works. And what we can see is that the landslide has been reactivated and extended and expanded. So this is the landslide I showed you before, this area here. What we can see here is the velocity in millimeters per year with a green color showing relative stability, and the orange and red colors, the yellow colors, show increasing movements. This is done completely remotely from the satellite data, but it shows you the extent of the area affected and also the magnitude. So what we can see here is this area, even though it's been mitigated, the landslide seems to have recently expanded and extended into this area. So by selecting each of these points, here, here, and there, we can see the behavior of these points. So the first point, which is the red one, is shown here, has reached between 2017 and end of 2018, almost 15 millimeters. The blue point, the yellow point, which is in the blue circle, is this one here. And I wanted to also compare with a point on the other side of the landslide, which remains stable, which has a velocity, a mean annual velocity of 0.5 millimeters per year. So you can see that this point is actually stable. For each of these points, you can get their location in latitude, longitude, and the velocity. And as I showed, and I'll show in the next examples as well, you get these outputs in a graphical and also in a tabular format. This is an example for a monitoring of a dam. So again, similarly, we performed an analysis of this dam, and you can see it here that the highest displacements are along the section with the highest point along the dam, and you get this characteristic oval shape here, which are the highest movements of the dam. Again, the red colors are the highest movements, the green are the smallest movements. And by selecting each of these dots that are shown here, you can see how much each of these points is moving over time. We did this analysis from December 2014 to after in 2018. So you can see along the highest points on the dam, how each of these points are moving. And in that way, you can identify if there are any problematic locations, and you can install sensors for getting higher accuracy of data. So because this methodology has wider coverage, so with one single analysis, you can cover wide areas, you can identify your problematic locations, and in that way, you can install your sensors because you might have an area where you don't know you have problems. This is an example from Joshimath in India of the landslides. So again, we can see the annual velocity in millimeters per year here. I will concentrate in this area first, which we have extremely high movements. And by selecting, let's see this point here, we can see that the velocity exceeds 140 millimeters per year. So reaching almost 300 millimeters. In this urban area, we can see some buildings over here. So you see the location, the velocity, the values in table. Always our first measurement is our zero, and we can see how these displacements are increasing over time. You can print these values, you can export them in or copy them in CSV. Also, interestingly, I will show you these locations here, which are again in urban areas. We have red points and blue points. The difference between the red and the blue have to do with where the satellite is. So red means the movement is away from the satellite. So this red point here, because of the geometry, it's moving, the satellite is from this direction, so it's moving away from the satellite. The distance between our satellite and the ground is increasing. Because of the slope here, these blue points are going towards the direction of the lands of the satellite. The important thing here is this is the red point, this is the blue point I'm showing here. So what we can see is that we started the analysis in January 2021 up to the end of 2022, and we can see that there has been an acceleration in the movements. At the beginning, there was little movement, and something happened around this period. And also around here, we can see an acceleration in the displacements. So you can detect the trends. This is an example here from a railway line. So we can see the difference between sections that are shown green and sections that are shown orange-red. The green sections are relatively stable. The yellow and orange sections are having some displacement issues. In that way, the railways are good scatterers. So you could see we got a lot of points along this railway line, and this is with the free data. And you can identify, as I said before, because of the wide coverage, where you might have issues. And in that way, you can prioritize your maintenance, as well as taking you know, where your resources should be allocated to which sections. So for example, this is more green color, so it's more stable. The yellow orange, we have issues. So this red circle here reflects this one, and a few meters away is this green point here surrounded by the blue circle, which is relatively stable with velocity of 0.5 millimeters per year. And this is an example from expansive clays and how they affect the structures and the buildings. So this is a school, and what we can see here is a great seasonality in the measurements, with about 10 millimeters reaching maximum. So we can see great seasonality, and same goes to these points over here. So actually, if you visit this specific school, you see big cracks and problems on the structure. And let me now show you through the platform. We have some other examples. So I will start with this example. So this is an example in Fujairah. It's a road, it's a highway connecting Dubai and Fujairah in UAE. So you can see this here. And we have performed an analysis in both ascending and descending, as I showed you at the beginning. And that allowed us to decompose that and get the true vertical displacements for a period of 2014 to 2018. And straight away, you can see the green are stable areas. And here in this embankment, we can see increasing movements. And we can plot a profile and see the increasing, how these movements are behaving. So we can see this is a vertical displacement around 0. And here we have increased displacements and going back towards 0 again after this embankment. I will show you now an example from Austin, Texas. So in this example, we wanted to monitor the road network. So you can see points only along the road and not in the building, because we clip the data to represent only the buildings, sorry, only the roads. And the important thing of this is that straight away you can identify which parts of the road network have greater issues. The green are the parts of the road network that are stable, and the yellow and orange, again, they have some issues. But let's see what the problems are. This is an example where we have seasonality in the movements because of expansive clays. And this is shown here. This is a displacement with uplift, subsidence, uplift, and subsidence. And these data coincide very well with the rainfall data. So we compare our outputs with the rainfall data. And actually in this area in Austin, Texas, in Taylor, Austin, Texas, it's raining around April, May is the maximum rainfall. So that's why we get the uplift around this period. We can combine this with other data. Let's select the yellow point here, and let's select also a stable point. So let's select this point here. So we have 1, 2, 3 points. They are very close together, but they have a different behavior. So again, this is a good way for identifying the problem, but also get the actual magnitude of the issue. And next, I will show a sheet pile wall in Jeddah we monitored. And this one, we got the horizontal, what I'm showing here is the horizontal displacement. So you remember I mentioned we have ascending, descending, we decompose and we get the results of vertical and horizontal. So what I'm showing here is the horizontal displacement in millimeters of the sheet pile wall between 2019 and 2021. What do the colors show? The red shows movements westwards. So the red color shows that in the center of this wall, the movements are moving in the west direction. But let's see the magnitude of these movements. With this profiling tool, we can draw a profile here and see the displacements in millimeters, and we can see that, okay, we have strong horizontal movements in this part of the wall. Okay. And let me go back to the presentation now. Okay. Now, what happens if we want to get a point, those points I showed you, a measurement of the displacement, and we cannot obtain a dot because we don't have a control over the points we get measurements from. In that case, if we want to guarantee a measurement on a specific location, we install corner reflectors, which are metallic trihedral structures, and they have to be designed in a way to so that they can have a view towards the satellite, they're pointing in the right direction, and they have to have the right dimensions, which we always check before their construction. They have to be depending on the surroundings to make sure that their signal is dominating the surrounding area to ensure we get a measurement at that specific location. And now I will show you some results from our soil moisture algorithm we developed via satellite data. So this is the soil moisture algorithm showing the in situ soil moisture data versus the algorithm soil moisture data extracted with quite a good correlation, especially for the values up to 50% of volumetric soil moisture content. And we use this type of data. The in situ data are over more than 3 years of data, global data. And the reason I emphasize in this more than 3 years of data is to show that we capture the seasonality of the soil moisture in our algorithm as well. And this algorithm can be applied anywhere, globally, anywhere in the world. And I will show you one example. We recently applied it in Singapore. And the importance of that is we combined it in this example with displacement data for a case of a landslide. So we wanted to measure the soil moisture in this area here. These are the results from 20th of February 2023. You can see this is the soil moisture content values. We get quite low values with this color. You can see the legend here. And nearby, there was a meteorological station. So the rainfall data in millimeters are shown here. 20th of February, we are here. So you can see a little bit of rain only before 20th of February. And comparing this a few days later, we can see on 16th of March, a few days later, a big difference in the color scheme. So on 16th of March, we have higher values of soil moisture content, looking at darker color of blue. And we are now here, 16th of February. What we notice from our rainfall data is that a few days before we had a lot of rainfall in the area. And that's the reason for having these high values. The advantages of this algorithm is that you can have this data with every image acquisition, and you can have these values at the pixel level. And by drawing a profile, you can compare the soil moisture content between different dates, like the first date I showed and the second date I showed here. And also talking a little bit about the use of artificial intelligence for the susceptibility maps. I mentioned at the beginning, using the displacement information that I showed you, soil moisture information I showed you, and a lot of other parameters like topographical, hydrological, geological, and other information, we have developed a methodology and algorithms using AI for assessing susceptibility to landslides, and also for swelling clays, and also for sinkholes. All these geohazards are obtained via our IGIS, which is a web app. It's an infrastructure asset management platform. So it's a one solution for all geohazards, which enables to have regular and reliable asset surveys. You can have large networks, and allows this for early intervention and effective repairs and less disruption, because you can see the trends and the susceptibility early on before the occurrence of severe damages. And let me show you the susceptibility examples now. I have it open here anyway. So let's go to these two examples. I will show you California and also one in Cyprus. Okay. So first the one in Cyprus and then the California one. So what I'm showing here is a susceptibility map to landslides, shown in red. It's a high susceptibility, moderate, low, and no susceptibility. So in that way, you can identify areas that they have high susceptibility to landslides. And the advantage of that is that it can be easily updated to reflect the triggering of new landslides due to the weather effects, and therefore taking into account the climate change with intensive rainfall and different patterns. This is a comparison with traditional conventional landslide inventory map. So the blue boundaries show the registered landslides, and we can see that, for example, in here, this whole area has high susceptibility, and here we have moderate, but the registered landslides show these gaps here, but actually the whole area has high susceptibility. In some other examples here, the same as well. And the one we recently did in California. Okay, so again, we show a susceptibility map for large areas in California. And we also compare this with published maps with very good agreements. And these dots I show here are some registered landslides we found on the system. So let's go back to the presentation. Okay. And now I will present a few slides from my colleague Bala Rejut, who is also in this call. So this is some of his work. So this is for the Himalayan region. And so what we can see here, this is an analysis done on the glacier velocities using INSAR. And what we can see is the red colors show the higher movement of glaciers. So we can identify which glaciers are moving faster and which ones are stable, shown in blue. Also, looking at the coherence analysis, here we can see some medial moraines here, shown in this location here. And the importance of this, you can see here, and also obtained from this optical image here, is that you can predict which areas will be affected and by the glacier. So with the coherence analysis, you can identify these features within the glacier. And this is another coherence analysis shown here. So let me see that. So this shows low coherence area. So the low coherence means usually is associated with water. So someone might think that this is a water, but looking at this area, we can see that this is not actually water. This is looking at the optical data. This is water, but this is not water. This is a glacier that would be melting. So in that way, we can identify using INSAR and satellite remote sensing techniques which areas are at a higher risk of melting of glaciers. So that's all from me, and thank you very much. This is my email address here if anybody thinks of any questions later, but I will be happy to have a discussion now and anything you would like to ask.
Yeah, thank you so much, Dr. Skevi. I think that there are some questions in the chat box. If
Yes.
see that and answer, then it will be nice.
Mm-hmm. Okay, let me just see. Okay.
Carlos?
Yes, I can see a question here from Carlos. Is how do we know we are comparing the same points at the different epochs? Okay, that's a good question. We know that we are comparing the same points because for a point to be detected, it has to have high coherence and reappear in successive images. So if we have, for example, highly densely vegetated areas where the vegetation grows, then gets mature, then gets harvested if it's agricultural land, the points will not, it will be difficult to get points in those areas, and we will not get any points. So the answer is that the points are points that are detected as the same ones with every successive image, with the majority of the successive images. Also, a question is how accurate are the coordinates of the points? Again, that's a very good question. This depends on the source of the satellite data. The examples I showed you for this presentation are with the free satellite data that they have, even though they have 2 to 4 millimeters accuracy of displacement in terms of spatial resolution, they are about 10 meters spatial resolution. But there are commercial data with improved spatial resolution of about 3 meter, 1 meter, or sub-meter resolution. So that actually depends on the source of the data. What is the normal thickness and weight of the corner reflector? Okay, that's a good question. I haven't. The thickness is not very thick because they are metal sheets. Actually, they don't have to be very thick. It's the dimensions that they're important. The ones I showed in the example are about 1 meter for each dimension, and the one I showed, it had a big base to concrete base to keep on the ground. You don't need such a big base. You can put them on walls with some brackets or with a small base just to be on the ground. They are not very heavy because we installed a lot of them, but I'm not sure exactly how much. If you are interested to find out more about that, send me an email and I can send you information about that. I don't know if we have any other questions.
Yeah, actually, participants, if you have any questions, you can unmute and just ask Dr. Skevi.
Hello, how do you measure the vertical distance, vertical displacement?
Yes, sorry, what I didn't hear the question. What do you want to know about the vertical displacement?
Yeah, you can repeat your question, please.
Yes.
Okay.
Hello,
I think
Doctor. Ma'am, I have two questions.
Yeah, please, a bit louder.
Ma'am, I have two questions vis-a-vis INSA is concerned. The first question is that regarding the soil moisture content that you were discussing. So let's see if there is a torrential rainfall and it goes for like 1 or 2 days. And as far as INSA data is concerned, especially for Sentinel, the time period it takes the data from the same place, it varies 4 to 5 days or sometimes 10 days. So by that time, I think the level of the water table will decrease to somewhat extent. So how does we look into the accuracy, like how accurate is the data for soil moisture content?
Yes. You are correct with that. The satellite depends on when there is satellite data available. The availability at the moment is every few days. So we have new data every few days and we compare them with the in situ data at the same days. So that's how we got the correlation. But I agree with you, it will not reflect, if you have strong rainfall one day and then the satellite data are 4 or 5 days later, it will not reflect that specific point that it rained, but it will show the impact on the day you collect the data. So the soil moisture data is on the date of image acquisition we collect. And that's a limitation because it's not an in situ sensor. You're making a good point. Each method has a different advantages. The in situ sensor will collect all the time the data. The satellite data will collect it only when there is a satellite image passing, which is every few days, but it will have a wider coverage.
Yes, yes, ma'am. And one more question,
Yes.
Like the resolution of the Sentinel, so it varies somewhere around 5 meters. And when we say that we are measuring the deformation, so like the size, like the resolution is much higher than the deformation. It might be higher, like something. So how accurate is that? Like, can we exactly measure the deformation? For example, you showed us a sheet pile wall, and there was a deformation for some or something. So that is too less. So are we exactly measuring that deformation using the INSA data, or we have some sensors that are installed in that sheet pile walls?
on that specific wall I showed, there were no in situ data. The data I showed, they were only from the satellite data. And as I said, the outputs are with millimetric accuracy. Of course, for every analysis, we know the precision of each analysis because it will depend on the number of images we use, on the atmospheric effects and all that. We had examples of embankment monitoring and other examples where we compare them and combine them rather with the in situ measurements. So if in situ measurements are available, we sometimes combine them, yes.
Thanks, Tom.
Hello.
Yeah.
Yes, hello.
Yeah. Asha, have you ever tried to confirm what these movement you are getting from satellites? Have you tried to confirm them on ground?
Yes. A good question. As I said, for some of the projects, even some recent projects we did for embankments, and we have in situ sensors installed by different providers, and we combine them with our data. We have also done this in mining, where we combine the outputs with the in situ sensors with very good results. I can maybe I can share some outputs, but yes, there are with some good correlations, I would say.
Again, I was asking a question. How do you measure, because on a slope movement will be horizontal as well as vertical. How you measure vertical movement?
Yes. Okay, the vertical movement is measured if you have results from two different analyses. So if you have measurements from the ascending and from the descending, you can decompose them geometrically and get the vertical component of the movement, because the satellite actually measures along the satellite line of sight. So let me just, yes, it measures, sorry, let's find the, this is the line of sight. So it measures along this direction. If we have it the same on the opposite direction, like here, we can decompose this and get the vertical component of these measurements and the horizontal. That's how we get the vertical.
Oh,
you need to have two directions. Yes.
Thank you.
You're welcome.
Dr. Skevi, there are some more questions in the chat box.
Yes, let me see.
I think somebody is asking for the feedback link. So there is no feedback link. Okay, if you have anything to write, you can write to us back. Yeah,
yes, or they can send me an email later if they don't think now, or in the chat. I will be happy, or even after this call, if they can send me. So if I can see now, relating back to Carlos' question, what makes a point unique so that you are certain that you are measuring the same point? Okay, the reason I know it's the same point is because if it's not the same point, the point will not appear in my analysis. What I mean is that, let's see here. For this point to appear here, it means its signal is constant in successive images. Otherwise, it will not appear. If it's something that changes a lot in terms of the signal, this point will not appear in the same image. So that's how we know the point we're measuring. If we analyze 2 years of data and we get one point on one location, it's the same point 2 years ago and the last image used. The reason is, as I said, this is defined by the coherence. If the coherence means its signal, it keeps appearing in the successive images. It's not a vegetation, for example, that changes properties in terms of maturing, harvesting, and being healthy vegetation, that the signal will be different. In this one are points that they have constant signals, such as buildings, corner of buildings. That's why we tend to get very good outputs in urban areas. Okay, any other question? Okay, what are the procedures we should do to find out the vertical displacement? As I said before, you need to have the ascending and descending data and then decompose them. Are there books about INSAR? Definitely. There are a lot of books. I can share some. There are some good examples, either from the European Space Agency or from other sources. If you do a search, or you can send you some. Okay. Not sure if there are any other questions.
So participants, if there is no more questions, so we can close the session, Dr. Skevi. So thank you so much. So your email is already shared. So I think, if there is anything, I think they can contact you directly. So personally, I'm very thankful. I really enjoyed your presentation, and I'll be in touch with you because I'm interested with that Joshimath thing, because we have a real-time monitoring site there. We are doing at the ground level. So maybe if we can correlate something and, so.
Yes, be very interesting. Yes,
Yeah,
that would be one answer to a question, whether we validate them with the in situ, definitely.
Exactly. We have that on the very active slope. We have like a very dense network of sensors, extensometers. We have tilt sensors. We have a weather station. My student Kunal Gupta, he's working on the real-time monitoring data. So that's where I'm more interested in that. So we'll be in touch. Thank you so much for such a nice lecture. And so if there are no more thing, I extend my sincere thanks to you for your immediate acceptance to be one of the speaker, and to all the participants. Our lecture is also been scheduled in the month of November. So I'll let you know. So kindly register and keep getting the updates. So we have going to have a speaker from Norwegian Geotechnical Institute. So it's also going to be on offshore monitoring. So I think the lecture series are coming up really nice. I'm so glad to hear to different parts of the world from practitioners and also from the researchers. Thank you, everyone. Dr. Andrew, you want to add something?
Thank you very much, Neelima. Thank you, Skevi, for a very nice presentation. I really enjoyed it. It's very good to very well explained, and shows the huge application of the INSAR technique. I'm just going to share my screen quickly. I have some notices. Hopefully you can see my screen. This is just to repeat what we've said in the past, to remind you that there will be a workshop next June in Barcelona on field monitoring, and that will take place, as I said, in Barcelona. There will also be we're sort of finalizing now the program for a meeting and a workshop that will be held in Portugal, in Lisbon, during the European Conference on Soil Mechanics and Geotechnical Engineering. That will take place on Sunday, the 25th of August. We're currently, like I say, working on the program and hope to be able to release that very soon. Just a reminder that if you want any information about the TC220, you can get it from the ISSMGE website, or from our own dedicated website at fieldmonitoring.org, and that you can follow us on LinkedIn, which is where you'll find out most of the information about things that are happening. I'm pleased to say that we now have 270 followers, so we are growing each month, and I'm sure that's largely due to this international lecture series. So thank you, Neelima, for organizing that. And hopefully next month we'll be up into the 400 and 500s. So thank you very much again, and look forward to seeing you next time.
Thank you so much, Dr. Andrew. And one more thing, 2026 we will be having an international conference in field monitoring. That is at IIT Indore. So please follow us for the updates. And this TC220 is one of the very young TC and a very active TC group under the leadership of Dr. Andrew. So if you are not a member of ISMG, I suggest you to take the membership. And if you're not member of Indian Geotechnical Society also, just go to the webpage and you can take the membership, because a lot of things are coming up. We are really dynamic in doing a lot of activities, and so it will be very helpful. So